Hi everyone, Mr. S here. In this video I'm going to be talking about pH, and specifically these 6 topics, which we'll revisit at the end to make sure we understand them. So let's just jump right into it. In order to understand pH, I have to first understand what's called the hydronium ion. This is very important. So a hydronium ion, you should write this down, H3O with a charge of plus. A hydronium ion is actually what makes an acid an acid. Now, what does hydronium look like? Well, it kind of looks like water, right? If you take water, how would you turn water into hydronium? Well, you need to add an H and you need to add a plus. And we've already talked about this a lot with acids. First of all acids have to be water-based, aqueous, and acids produce, according to the Arrhenius definition, they produce H plus ions in water. What's another name for H plus ion? Proton. And by the Bronson-Lowry definition, an acid is a proton donor. So you can see how H plus being given to a water can form hydronium. Now, why would water want to bond with an H plus? Because don't things always want to get to a balanced neutral state? You know, like Na plus and Cl minus, once they find each other, that's NaCl, they're happy. Well, why would water want to bond to a proton? Well, let's look at water. Water is H2O. We represent it like this. And remember, in a more detailed picture, here's my oxygen atom. Here's my hydrogen atom. Here's my hydrogen atom. And we've talked about the polarity of water before. Remember, there's an uneven distribution of these electrons, an uneven share. The oxygen is pulling those electrons closer to itself, giving it a partially negative charge. Now, if you don't know what that symbol means, it's the symbol for partial. It looks like you're writing an 8, but you get bored 3/4 of the way through. So that's a partially negative charge, giving these hydrogens a partially positive charge. And we just kind of represent that by saying minus, plus, plus. But in reality, these aren't full charges like ions. These are partial charges. Now, why would a water be attracted to a proton? Because like everything else in chemistry, it's all about those opposite charges attracting. So the positive charge of the proton will be attracted to the negative, partial negative charge of this oxygen, and that H plus will actually stick onto it and bond to it, forming our H3O plus, where this now represents, let me draw it here. This would now have a third hydrogen on it. But the entire, it's not a molecule, it's an ion. The entire ion has an overall charge of plus because it's not bonding with just an H, it's bonding with an H plus. So the idea here is we have H3O with a charge of plus. So that's a hydronium ion. Let's talk about how hydronium actually kind of takes place and forms. And we'll start with something called the self-ionization of water. Self-ionization. Ionization sounds like a fancy word, but really, you know what an ion is. It's a charged particle, charged atom. Self-ionization means when it turns itself into ions. Self-ionization of water. So if we have a sample of water, H2O, let's say this water molecule happens to encounter another water molecule, just the right speed, just the right angle, all the stars align, and it's exactly perfect. Well, what can happen is, let's say these are our 2 water molecules. What can happen is this water will strike this water perfectly and can actually steal the proton from this water. Because remember, here is an H plus on the end of this, the line represents a covalently bonded hydrogen ion, hydrogen atom. So what can happen is this can pick up the proton, leave the electrons behind, essentially steal the H plus. And notice this would now be our H3O with an overall charge of plus. And the hydrogen just got plucked off. Look what we're left with, OH. But it wasn't the entire H. It wasn't the proton and the electron. It was just the proton. If you take a positive charge away, what's left? Minus. So this is OH minus, should look familiar to you, hydroxide. This is H3O plus, should look familiar to you now, that's hydronium. So water can naturally split up into hydroxide and hydronium. Now, this isn't a permanent process. It can go backwards as well, where these can now happen to strike each other or different ones again, and that proton will go back with the original one. So in fact, we write a double arrow here showing it goes one way, but then it can also come back. And this is a rare process. They estimate that in regular, like 25 degrees Celsius water, at any given time, about 1 in 10 million water molecules are currently ionized, are currently split into hydroxide and hydronium. And when it comes to acids, the important one is this, hydronium. And how much hydronium something has it determines its acidity and is measured in the pH scale. Now, this is regular water. It didn't become more acidic here just by splitting up, because in fact there's an equal proportion of hydroxide. So this is normal water, natural water. And what's the pH of natural water? 7, right? pH equals 7. Well, why 7? I always ask my classes that, why 7? You know, out of all the numbers they could have gone with 7. And the answer they usually get is, well, it's half of 14, and the pH scale is at a 14. Well, you know where I'm going with this. Why 14? And it's not as random as you might think. And in fact, some of you might be able to look at this and say, oh, I see where the 7 comes from. Let's go into a little more detail. When we're talking about the pH scale, we are mathematically measuring the concentration of hydronium ions. And in fact, something I need to point out here, the phrase concentration of can be written as brackets. So when I say the concentration of H3O plus ions, this can be written as bracket H3O plus bracket. And this is something that's very common in acid writing, so you should be familiar with that. So the concentration of H3O plus. So what I'm getting at is pH is a way of measuring the concentration of H3O plus. But if we didn't use a pH scale, you didn't have to. I would be able to look at water and say, hey, don't worry, that's not very acidic. It has a hydronium ion concentration of 1 in 10 million. But that's a really weird way of saying it, right? And the number 1 in 10 million, that's it's annoying to have to write that number. I mean, my stylus is running out of ink here writing 1 in 10 million all these times. It's a joke, by the way. 1 in 10 million. So what's another simpler way I can write 1 in 10 million? Well, first of all, 10 million, that's a lot of zeros. Let's write that in scientific notation. This would be 1 in 10 to the 1, 2, 3, 4, 5, 6, 7, because remember it's 1 times 10 to the 7th, not 10 times 10 to the 7th. So it would be 1 in 10 to the 7th. May have rung a little light bulb for some of you about where pH of 7 comes from. So 1 in 10 to the 7th. Another way of writing 1 in 10 to the 7th, because if we're applying a mathematical formula, you can't have words here, 1 in 10 to the 7th. Well, this would just be 1 over 10 to the 7th, like 1 out of 10 to the 7th. But my classes know this about me. I hate denominators. I always want them to go away. How can I mathematically rewrite 1 over 10 to the 7th to be something a little more user-friendly? Well, some of you guys who have more experience with exponents might know that 1 over 10 to the 7th can be written as 10 to the negative 7th. And in fact, this 1 in 10 million can be easily written as 10 to the negative 7th. So it makes it a little easier, because I can now say to someone, don't worry about that water. It's got a hydronium ion concentration of 10 to the negative 7th. But even that is a little, cumbersome to say. So we developed the pH scale to put this, which is really a ridiculously small number, it's 0.000001, in a kind of a regular number sense. And we use a logarithmic scale for this. Now, you may have actually seen logarithmic scales in the past few weeks when we're plotting things like COVID-19 cases. Very quickly, in the US, it went up to something like 500,000. I should look that number before I say that. But it's a very high number, and it happened very quickly. So when they were plotting it by date, you may have seen a graph that may have looked something like this. And hopefully we're seeing it level off. Well, If this were a linear scale, meaning like 100, 200, 300, 400, it would not look like this. In fact, it would look like it was like so straight up that it's hard to actually see the number. So that we often use logarithmic scales to display this. And in a logarithmic scale, this would be like 1. This would be like the number of cases, and these are the days. Usually the days are linear. So this would be like, March 25th, March 26th, and so on. It'd be like a 1, 10, 100, 1,000, 10,000, and so on. And you can see that every time you go up by 1, it becomes 10 times larger. This is not an exponential scale. Exponential would be like 2, 4, 16. This is much more drastic. This is 10 times bigger every number. So that's a logarithmic scale that you may have seen recently in the news. pH is a logarithmic scale as well. And in fact, the formula for it, and here's where we're going to actually write our formula. pH, get that box out of there. Oh boy. pH equals negative log of the hydronium ion concentration. Now, raise your hand. I can't see you, but raise your hand if you've studied logs in math. I'm assuming about a third of you have your hands up. That's okay. Even if you've never touched logs, I'll go over them very briefly, and we're not going to be going too deep into the math behind these. Logs. Log stands for logarithm. If I were to ask you something like this, log of 100 equals x, and I said solve for x. What this really means is there's like a little invisible number down there, and unless I say otherwise, it's a 10. This stands for log of base 10. And base 10 means like our number scale is based on 10 numbers. You go up to 10, and then you're like 1, 0 to 9, and then you restart. So it's every 10. So what this really means is 10, the base 10, raised how many times would give us this number? Or in other words, 10 multiplied by 10, how many times would give us 100? And I could write that as 10 to the what power equals 100. And I'll bet you can all give me that answer. 10 to the what power gives me 100. 10 times 10, how many times? Well, twice. X is 2. So in fact, if you plug into your calculator, you will have a log button, L-O-G, on your calculator, or if you don't have a scientific calculator, you can just Google it, log, parentheses, 100, close parentheses, hit enter, and it will tell you 2, because 10 raised to the second power gives you 100. Let's do another example. Let's do, what if I say log of 10,000 equals x? Well, let's work out what x is. What this means is 10 raised to what power is going to equal 10,000. We could work this out in our head. 10 to the second is 100, then times another 10, that'd be 3. That's 100 times 10 is 1,000. And then times another 10, that's 4 tens, that's 10,000. And that's what we're going for. So the answer here is 4. So if you go log of 10,000, let me double check that I'm not making a mistake here, log of 10,000 equals 4. So going back to my formula here, we can relate logs to pH and the purpose of this is to take a really complicated and ridiculously small number like 1 in 10 million, because remember, this is 0.0000001. It's to take this ridiculous, hard to understand, hard to write, and bulky number and turn it into a nice user-friendly number like 7. Here's how we do that. pH is negative, oh boy, I just realized there's a button on my stylus, which I didn't actually realize was there. Hold on. Okay, pH equals negative log of the hydronium ion concentration. And we just determined in the other slide that in regular water, this is 1 in 10 million, or 1 in 10 to the 7th, or 1 over 10 to the 7th, or 10 to the negative 7th. Let's rewrite it in that last form. pH equals negative log of 10 to the negative 7th. Now, why did I go from brackets to parentheses? Because brackets means concentration of, it's like a chemistry term. If you're just finding the log of something, you generally just use parentheses here. All right, Negative log of 10 to the 7th. Let's, for a minute, let's just erase that negative in front and just work this out and see what we get. So if I were to say log of 10 to the negative 7th, what that really means is 10 raised to the what power equals what's in this parentheses, which is 10 to the negative 7th. 10 to the what power equals 10 to the negative 7th. It's almost like it can't be that easy, but it is. X equals negative 7. 10 to the negative 7 equals 10 to the negative 7. But remember, the formula for pH is not log of 10 to the negative, or log of H3O plus, it's negative log. So you take whatever you get, you multiply it by -1. What's negative 7 times negative 1? You just cancel the negative out, and there's your 7. So why is 7 the midpoint? It's because in water, the concentration of hydronium is 1 in 10 million, and 10 million is 10 to the 7th, or it's 1 in 10 to the 7th. So that's where that 7 comes from. By the way, I should mention one thing here. For concentration, it's technically a measure of molarity. So when I say it's 10 to the negative 7th, technically it's 0.0000001 molar. So this has a unit, concentration has a unit, which is molarity, but pH doesn't actually have a unit, it's just a number. It's almost like a, this is not necessarily like a ratio. You can think of it like a ratio because it's like the ratio of hydronium to water. So pH has no number, concentration has a unit of molarity. Let's do one more example where we solve for a pH. Let's say we took our water and we added a tiny bit of acid to it, and it actually became 10 times more concentrated with that acid ion, which is the hydronium ion. So the concentration or the molarity of H3O plus went from 1 in 10 million, which is water. And if I were to make this 10 times more concentrated, now it's going to be 1 in what? Not 10 million, but 1 million. And not the other way. If you went the other way and went 1 in 100 million, that's actually 10 times less concentrated. So now it's 1 in 1 million. So the H3O plus concentration can be rewritten as 1 in 10 million. Sorry, that's 1 million. What is this in scientific notation? 1, 2, 3, 4, 5, 6. 1 times 10 to the 6th, or just 10 to the 6th. So 1 in 10 to the 6th is 1 over 10 to the 6th, and that can be written as negative log of 10 to the negative 6th. Really quickly, again, you're doing the same thing you did with 7 before. You go 1 in a million, which is 10 to the 6th, 1 over 10 to the 6th, aka 10 to the negative 6th. So my concentration, my molarity of H3O plus hydronium ion is negative log of 10 to the negative 6th. What's log of 10 to the negative 6th? 10 raised to what power gives us 10 raised to negative 6? Well, the answer is negative 6. But because we have the negative in front, we make it positive. In fact, you can take your calculator and type in negative, make sure you do negative, not minus, negative log 10 to the negative 6, close parentheses, it'll tell you 6. So notice what happened with our pH. When we were at 1 in 10 million, what was my pH of water? 7. We made it 10 times more acidic. Look at my new pH, 6. See how that makes sense? Remember that, or I think I erased it, that coronavirus graph where every time you go up one space, it's 10 times bigger. That's the exact same thing with the pH scale. When you become more acidic, meaning starting at 7 and go down, for every number you drop, it becomes 10 times more acidic. And that's one of the major points I want you to understand about the pH scale. If we have a pH scale here with 7 in the middle, and you go down to a 6, that's 10 times more acidic. Or if you go the other way, it's 10 times less acidic, or 10 times more basic. And we proved it right here with the numbers. You might think that if you start with a 7 and want to make it 10 times more acidic, you divide it by 10 and pH would be 0.7. No. In fact, for pH to be 0.7, well, let's go with an actual, a whole number. It'll make it easier. Let's say we wanted to show a pH of 1, which would be very acidic. This is 5, 4, 3, 2, oh boy. 1. How many times more acidic if you go from 7 to 1? All right, well, 7 to 6 is 10 times. 6 to 5 is 10 times. 5 to 4, 10 times. 4 to 3, 10 times. 3 to 2, 10 times. And 2 to 1, 10 times. Now, how many times is that? You might say 60. But it's not 60 times because you don't add these. It's 10 times and then times another 10. So this is 100 times, 1,000 times, 10,000, 100,000, a million. To go from neutral water to a pH of 1 million times more acidic. So you can see how a logarithmic scale works, where every number you shift is 1. You may have also heard of the scale they use to measure earthquakes. Probably heard of it called the Richter scale. It's actually an outdated term. They don't use the Richter scale. It's called the moment magnitude scale. It's a little bit updated, but it's still a logarithmic scale. So if you hear about let's say there's a 7.3 earthquake, magnitude earthquake, that's very powerful. Like if that were to strike in a major area, you'd be talking about utter catastrophic damage. One of the strongest earthquakes of my lifetime was off the coast of Chile. And it was an 8.3. You might say, well, all right, 7.3 is bad. 8.3, what's that, like 15% higher maybe? 10, 15%? No. How many times bigger is that? 10 times. That's 10 times stronger. In fact, it's very lucky that this did not happen in a populated area. 10 times stronger. So that's a logarithmic scale. Okay, so let's go back to the title slide here and just see what we've covered and what we still need to brush up on here. So we covered the hydronium ion, self-ionization of water, where 7 comes from, and the pH formula. All right, this shouldn't take us too long. Calculating pH of examples of acids. So let's say we have a 0.0395 molar nitric acid sample. Nitric acid. Now, nitric acid, I'll tell you, is a strong acid, and that's important for this. Strong acid. What does a strong acid mean? That it's really concentrated? No. Strength of an acid has nothing to do with its concentration. You could take a drop of nitric acid, put it in a swimming pool. That swimming pool is considered a strong acid. So a strong nitric acid, and this is my molarity. Now, if I'm asking for the pH of this, what's pH? pH is negative log of the concentration of hydronium ions. Well, I didn't give you concentration of hydronium. I gave you the molarity of the acid. But if we think about this, nitric acid is HNO3 aqueous. What happens as soon as that hits the water? Well, it ionizes, right? The water picks it apart into H plus and NO3 minus. And these are both now ions floating around. Now, H plus, that is that proton. And I told you in the slide, I forget where it was, but I said as soon as that hits the water, it's going to bond with water. In fact, there's an example. I don't think I used it in this video. Forgive me if I did. It'd be like if I took a bunch of $100 bills and just threw them in the cafeteria. Would they just sit there? No, they would immediately be picked up because they're a very valuable commodity. Well, when you take protons, H pluses, and put them in water, they're going to be immediately picked up by water molecules because they're a very valuable commodity. So these will very quickly turn right into H3O plus ions, aqueous, by bonding with water. So notice, for every one HNO3 acid formula unit, you're going to get one nitrate and one hydronium. Not half and half. This becomes one nitrate and one H plus, which becomes hydronium. So if I give you the molarity, the concentration of the nitric acid, because it's a 1-to-1 proportion here, you can even think of it like a mole ratio, I guess it is, then that's also going to be my molarity of H3O plus. So in this case, it's going to be negative log of my, in fact, I'm going to take the bracket out because I'm using the number now. It's negative log of 0.0395. Plug that into your calculator or plug it into Google. Negative log 0.0395. My pH is, and because I have 3 sig figs here, I want to report this with 3 sig figs, 1.40. which is very, very concentrated. Okay. Now, what I did here, the one-to-one, this only works when it's a strong acid. Why is that? Because a strong acid fully splits up into ions. If this were a weak acid, like acetic acid or hydrofluoric acid, well, not all of it's going to split up. Only a certain percentage of it will. So you would actually have to look in a reference manual at the temperature of the water and the initial concentration, and it'll give you a K value, which is basically like a percentage. It'll say like, well, 4.73% of it will be ionized, so you use that. And we're not going to cover that in Chem 1-2. You know, even if we weren't doing this e-learning, we don't touch that. So we deal with just strong acids. So when we tell you it's a strong acid, it means it will fully split up. I'll even write that in. Fully, okay, 3 L's in my fully split up. Okay. And the other assumption here, well, not an assumption, the other important point is that this is a monoprotic acid. When I say mono, what is that? One. Protic, what does that sound like? Proton. And what is a proton? H+. So this is a monoprotic acid, meaning it has one H+ that it's going to give. So that's why it's a 1-to-1 proportion. Let's look at a different acid. Let's go with sulfuric acid. Let's say we have a 0.0789 molar sulfuric acid solution, which is H2SO4, aqueous. Well, this is a strong acid, which you hopefully have that written down from before, strong acid, which means it's going to fully split up. Now, there is a little assumption here. I'm just going to kind of plant this seed and then not worry about it for the rest of the year. When I say this is a strong acid, technically it doesn't fully split up into H+ twice and SO4, because you might see where we're going with this. This is going to split up into H+. Okay, I click the button on my stylus. This is going to fully split up into, hold on, H+, another H+, because there's two of them, and sulfate. Now, in reality, when we say this is a strong acid, it's actually only going to split into one of these H+, and the resulting anion is going to be HSO4-, and that one actually will not fully split up into its second one. Sometimes it'll actually revert back into this. Let's ignore that assumption and just assume that it fully splits into two H+ and one SO4 2-. Now remember, each of these are going to form H3O+, and this is still going to be sulfate. So notice, for every H2SO4, for every one of these, you're going to produce one sulfate, which we don't care about in pH calculations, and two hydroniums. So this is now a 1-to-2 because this is a diprotic acid. So it's a strong acid and it's diprotic. So if I give you the molarity of the acid as 0.0789 molar, and I ask for the pH, well, pH is negative log of 0.0789. Oops, sorry, that's not entirely correct. I meant to say it's negative log of the hydronium ion concentration, H3O+. Well, in this case, for every one of these, I'm going to get twice as much hydronium. So what do I do with my initial molarity of the sulfuric acid? I'm going to double it, because for every one of these, I'm going to get two H3O+. So if I go times 2, that's going to give me 0.079 times 2, 0.158. And that is actually going to be my concentration of hydronium. So negative log of 0.158, which gives me, with 3 sig figs, 0.801. Oh, I put an M for molar. That is not correct. pH is just a number, no unit. It's my pH. Notice we are less than 1. 1 means nothing in terms of pH. It's not like a boundary or anything. Okay. One last quick example. You guys did the types of reactions lab back in, I think it was February, and we worked with acid, and it was very concentrated. It was 6 molar HCl. Let's call it 6.0. 6.0 molar HCl. HCl is a strong acid, which means the concentration of the molarity or concentration of the H3O plus is going to be the same as the 6.0 for the acid. Because remember, this will produce one H3O plus and one Cl minus. So the molarity of the acid equals the molarity of the hydronium. So let's find the pH. pH equals negative log of the hydronium concentration, which is 6.0. Oh, let me just write my answer out. All right, in your calculator or in Google, negative log of 6, negative 0.78 with two sig figs, negative 0.78. Notice how pH can actually be negative. If you have a concentrated enough sample, you will have a negative pH. Okay? There's one last thing we're going to cover. It'll just take a minute. Notice back in my slide with the self-ionization of water, wherever that ended up, right there, we formed hydronium, and that's what we've been working with for this entire video. But it forms something else too, hydroxide. And that hydroxide shouldn't be forgotten. We can measure the concentration of hydroxide just like we can measure the concentration of hydronium. Remember, pH is negative log of the concentration of hydronium, excuse me. pOH is what we can use to measure hydroxide. And it's a very similar formula, negative log of the concentration or molarity of hydroxide. Now, without doing an entirely other video on converting this, it's a very simple conversion. pH plus pOH is always going to equal a nice simple number, and that's going to be 14. And technically it's 14.000 forever. Perfect 14. So if you ever find the pH and look for the pOH, all you have to do is subtract 14 minus whatever you get. So for example, in this one here, if my pH was 0.801 and I'm looking for the pOH, 14 minus 0.801, it's going to be, let me see if we do this in my head, 13.799. No, 199. Just confirm that. 14 minus 0.801. Yes. And you use it however many decimal places you need in that 14. So in this case, 14.000 minus that gives me this. Okay, they always add to 14. And in this example, if my pH is negative 0.78, to find pOH, I'm going to say 14.00 minus negative 0.78. What is minus negative? That's plus, right? So look what my pOH is going to be. pOH is going to be 14.78. So pOH can actually be higher than 14. pH can be higher than 14 as well. If you have a very, very low concentration of hydronium ions, like in a very concentrated base, like a lot of the drain cleaners that you have at home, it's such a strong base that your concentration of hydronium is going to be so small that you end up with a pH of above 14. Okay, so we've covered all the major points that you need to understand for this cycle. Make sure you join your Zoom or Meet. If you have any more questions, good luck.